everyone, so welcome to the Dark Sky Project. My name is Oscar and we're doing a bit of a special event tonight. We're going to do a public outreach event and talk to you guys a bit about quasars, which are admittedly a very niche thing out there in the world of astrophysics, but hopefully by the end of the talk you guys will agree with me that they're actually really cool and incredibly important if you want to understand what's going on out there in the universe on the scale of galaxies. So how our Milky Way has evolved over time, as well as every other galaxy out there in the universe. And there's lots of things we can do with quasars as well, which are really, really important for astronomy today. So we're going to kind of go over the story of quasars, a little bit of kind of how we discovered about their existence, because it's a bit of a strange story, and it changed over time in a way that a lot of other things in astrophysics didn't really do. And then we're going to talk about what a quasar actually is and how the different aspects of it basically give us the effects that we see with our telescopes. And then eventually we're going to go into what quasars can actually do for us, how they're so important, how we can use them to study the universe, and what we might be looking to do with them in the future. So just a bit of housekeeping to start with. We have fire exits there, there. We're going to keep all these doors open to get a bit of airflow through because it is a very good day today. If you need to leave at any point during the talk, if you get a bit hot, or if you need a toilet or anything like that, please head out that way, the same way you came in. I'm going to leave that door open, so then you can head back in afterwards if you need to. Now, it is going to be a lot of information. I'm going to try and explain it as well as I can, but we'll pause every couple of slides, and if you have any questions, or you're not quite sure about something you'd like to try to explain, just let me know, and hopefully we'll understand a little bit more about these really, really cool black holes out there in the universe. So, I'm just going to put down the lights a little bit for some ambience, and let's get started. So, we're going to start the story of quasars at the beginning. And this happened shortly after the Second World War. Now, during this time, radar had been invented as a way to find enemy planes up in the sky. But when radar operators were doing this, they also found there were these bright blobs of radio light coming from space. So after the war ended, these radio telescopes were constructed. Here's one here. This is the 64-meter Parkes radio telescope over in Australia. This one was constructed in 1961, but there was a few kind of earlier generations before this. So we knew there was these radio sources out in the sky, and we set out to find them and map them. And this kind of accumulated with the third Cambridge Radio Catalogue, which was published in 1959. So we're seeing a section right here. This is showing a part of the sky. We have coordinates here and here, and these big blobs of radio light, because these at the time had really rubbish resolution. We weren't seeing kind of images like we see today, and like we see with colour telescopes and optical telescopes. We're just seeing these big blobs of radio signal coming out from space. So once you found this blob of radio light, we know that radio is just one part of the electromagnetic spectrum. So it's all light. Radio is kind of the lowest energy, the longest wavelengths, and then you go up to microwaves, infrared, visible light, which is what we actually see, and then up to UV, ultraviolet, X-rays, and gamma rays with really high energy light. But we can see pretty well invisible light as well. So what if we look at these same parts of the skies with our visible telescopes? So that's what astronomers did, and for almost all of these radio blobs of light, we found a galaxy out there. So that was a little bit unexpected, because these are really, really bright. In fact, the 4 brightest radio sources in the sky are all associated with galaxies. So we find these bright radio galaxies out there. We didn't know too much about them at the time. But we also looked at some places and we didn't find a galaxy at all. And a tentative kind of correlation was made with stars. And here we have one object here. This is 3C48, the 48th object in the 3rd Cambridge Radio Catalogue. And we have a tiny little star here in the middle of this image. And this is from a paper going, we've not found a galaxy here, but this is kind of the best guess of what could be emitting this radio source. And these stars were really weird. They were blue, very, very blue. They were changing brightness very quickly. They didn't seem to match any other kind of stars we knew of in the universe. So astronomers weren't convinced that they were stars. So the name quasi-stellar radio source was adopted, because it's kind of like a star, it's small, and it's emitting lots of radio light. Now, that is a big mouthful, so that was later shortened down to quasars. So these were the first quasars to be discovered. But we didn't really know much about them. So if we want to kind of find out more about a little point of light, what we can do is take a spectrum. So this is studying the universe through rainbows. And what we do is we take some white light, or the light from our star, which is all these kind of different wavelengths added together, and we split them using a prism, like we have here, or we can also use a diffraction rate. Now, this separates the light into different energies. So that's what we're seeing here. We have red light. This is the longest wavelength, the lowest energy. And then we come up, we find orange, yellow, green, and blue. And then finally, the purple. This is kind of the highest energy, very end of the visible spectrum. If we go this way, we find ultraviolet light. If we go this way, we find infrared light. Now, if we do this, we get this continuous spectrum. But for a lot of things out there in the universe, we're also going to see these lines. And we have two types of lines. We have emission and absorption lines. So emission lines, these come from hot gas, where the electrons of this gas is absorbing light, absorbing energy, and then re-emitting it. And it re-emits it in very specific ways. So we see these very specific lines in the spectrum. And a hydrogen in a lab, or in a gas cloud in space, or in a star, is going to give us these exact same lines. So this is the fingerprint of elements and molecules that we detect out there in the universe. If you've ever seen an article saying, we've detected a star and it's made of hydrogen and helium and carbon, whatever, this is how we know, because we find the spectral fingerprints in that light. We also see absorption spectrums as well. So this is kind of the opposite. Rather than hot gas emitting lights, now we have cool gas absorbing lights. But it's the same light, they're just dark this time rather than bright. So if we look at a star, it's going to give us something like this for a spectrum. This is the spectrum here, and then we graph the brightness over here against the wavelength of the colour, if you like, and we'll see the overall shape. This is telling us quite a lot about how the light of the star is emitted. We see all of these big dips. These are very big absorption lines as well from gas clouds that are maybe around that star or in between us and that star. So this is kind of what we can do with spectrum. So let's do this for these quasars then, these quasi-stellar radio sources. So this was done, and we found that these spectra, just like the sources themselves, were really, really weird. So here we have a graph. We have this purple line. This is the spectrum of a star. This is Vega. A star that we actually can't see from here in New Zealand, but you can see pretty well from the Northern Hemisphere. We then have this blue line, and this is the spectrum of a quasar 3C273. That quasar is going to come up again later. Now, in the star spectrum, we see the continuous line going all the way down, and we see these great big absorption lines. And you can see we have hydrogen beta, hydrogen alpha. This corresponds to dark clouds of hydrogen gas, maybe around the star, maybe in between. And then with the quasar, we see something completely different. We see lots of these tiny little spikes. These are emission lines, and also these little dips, these are absorption lines. And we have narrow lines like this, and we have these really big, broad lines like this. But even stranger, these lines, these didn't appear to match up with anything at all. We can take elements and molecules, we can make them glow in a laboratory and find out what their spectral fingerprints are, and this was the fingerprint of nothing that we'd ever seen before. So that was really, really strange. If we look at the shape of the whole spectrum as well, we find that stars have these kind of great big curves that go up and then go down like this over different wavelengths or different colours, whereas these quasars, they were kind of right or high in the very short wavelengths. They were glowing the blue and the ultraviolet. This tells us that there must be incredible amounts of temperatures. If you've got kind of glowing hot gas, this is going to be gas of tens of thousands of degrees. Now, you can kind of tell a little bit of information about the gas clouds that we have here by looking at the width of these lines. Because when we see them in the lab, we see these straight lines. They are very, very thick. But when we see them in space, they are not. And the reason for that is the gas that's creating this line here is moving. So this is due to what we call the Doppler effect. As that gas is moving towards us, the light gets compressed so that it looks higher frequency, lower wavelength. As it's moving away from us, it gets stretched out, the wavelength gets longer and lower frequency. And this has an effect of smearing out this emission line. This is the same Doppler effect, by the way, that causes an emergency vehicle siren to sound a little bit higher as it's coming towards you, and then lower as it's going away from you. So it works with sound and it works with light. So we can come up with an equation, which is this one down here. So this is working frequency, but we can do it in wavelength as well, where we have the width of the line divided by where the center of the peak is, gives us this relation here of the velocity divided by c, the speed of light. So we know what the speed of light is, we can measure this from the graph, so we can work out how fast the gas is moving. That's because of these lines. And if we do this, follow the narrow lines, we see that the gas is moving at 3 to 400 kilometers per second. So that's really fast. And stars in a galaxy move about 200 to 300 kilometers per second. So this is moving slightly faster than the stars within a galaxy. But here, these broad lines, we're seeing gas that's moving at tens of thousands of kilometers per second. Incredibly fast. We weren't sure actually how this could happen. There's going to be some kind of energetic event that's making this occur, but we didn't really know at the time. And the next revelation about quasars will come with this object here, 3C273. But before I go on to that, does anyone have any questions at this point? Anything I've not explained very well? All right, let's keep going then. So, 3C273. This object just up here, little radio floor, was in a very unique position in the sky, and that was because in 1962, the moon would pass in front of it. Now, we weren't exactly sure what we were looking at. We would make these tentative identifications with these quasars, these quasi-stellar radio sources. But maybe we were just getting it all wrong. Maybe we were looking at perhaps a background galaxy that we just couldn't see. So this was an opportunity to narrow down exactly where this source was. And I'm kind of going to demonstrate how this works. So we are looking up into the sky and we see this radio source out there, this big blob of light. We know it's going to be somewhere here, maybe. But there's lots and lots of stars here and lots of stuff going on if we zoom in, so we're not entirely sure. Now the moon is going to move in front of it, like this. And it was going to do this a few times over the year. So what we can do is we can train our radio telescopes on this part of the sky. And we can watch, because as the moon goes in front of it, it's going to block out this radio source. And that is going to disappear. So we're suddenly going to lose the detection. So if we time exactly when this happens, we can draw an imaginary line in the sky. We know that the moon must have blocked it out somewhere along this line. Then we're going to keep watching. The moon is going to move across the sky a little bit more, until eventually that radio source reappears out the other side. Then we draw a second line. So now, the moon is going to move across the sky, and we have two lines. And where they intersect, that's going to be where we can find our radio source. So, obviously, if we have something like this, we're going to probably be looking at this one here, where it's right in the center of highest amplitude. So, we have now detected our exact location. And as astronomers were observing this is kind of what we saw. We saw the radio signal increase, we look up, then decrease again. And this tells us there's actually two radio sources here. It's not just one object. And this is the highest resolution radio signal that we had achieved at the time, just because of that moon occultation, the moon passing in front. So we now have a location. So let's take an optical telescope and let's see what we can spot. So this was done with the 200-inch Hale telescope, at the time the largest telescope in the world. And they looked at this place and they found, once again, a little strange star, another one of these quasi-stellar radio sources. And it had this little line next to it as well. Now, the astronomer who was tasked with taking the spectrum of this star thought we were going to have a foreground star in our Milky Way, another one of these weird things that we don't know much about, and maybe one of these background radio galaxies. So these are our two sources. If we look down here, we have the Hubble Space Telescope image taken back in 2013, which is much higher resolution. We see the quasar here, and we see this is definitely not background galaxies. This is what we call a relativistic jet. We'll get on to why that's important in a second. So they started off with the star, they took a spectrum, and they found, once again, this really, really strange spectrum that didn't match up with anything we knew. Lots of these strong emission lines which we just didn't recognize. So Schmidt started writing the paper to publish, and then came back to it a couple of months later, looked at the spectrum, and then had a realization. And that is that actually we're seeing the spectral fingerprints of hydrogen, but not where they're meant to be. They have all been shifted by some amount. So that's what these red lines are showing here. So this one here is the hydrogen beta line, and it should be over here, this part of the spectrum. We're seeing it over here. And the same one with this one, and this one, and this one. And we're observing they are all shifted by a factor of 1.16. Now, if this was the case, if this was what was going on, then we would see the biggest, the strongest hydrogen line, the hydrogen alpha line, shifted all the way down into the infrared. Because this normally sits just about here in the graph. And if you go shift it down, it's going to go down over here. And we're going to need a special infrared spectrograph to be able to see it. So they got one of these, then hooked it up to the telescope, and sure enough, there was that line. So this is science in action. We've we've made a prediction, we've tested it, and we found this signal. So now we know we have a redshift. Now redshift can mean one of two things, because what this actually is the Doppler effect. Doppler effect coming back into play. So we've got something that's moving away from us, and so the light is being stretched out to longer, more red wavelengths. And that means each of these emission lines is going to get stretched out to the lower parts of the spectrum. Now, at the time, astronomers were assuming these were things in our Milky Way. But for something to be moving fast enough away from us to see this effect, it would have to be moving about 16% the speed of light, or 200,000 kilometers per second. I don't know how you could even do that with a star in the Milky Way. Maybe you could have some kind of weird gravitational interaction which slingshots that star out. But we found 7 or 8 of these things at this point. So that is incredibly unlikely to be happening for all of them. And all of these quasars have these really big redshifts observed. So the less impossible scenario is actually we're looking at something that's really far away. Now the universe is expanding, and this means that the further something is away from us, the faster it's going to be appearing to move away. So we categorize this by Hubble's law. That's what we have here, and this is a Hubble diagram. So we have the distance here on the bottom, we have the velocity here on the top, and so the further something goes away from us, the faster it is going to move away. So we can use this relation to get an idea of the distance to something from an observed redshift. Now, the distance here is roughly given by the speed of light times the redshift factor, so that's this little kind of shift here, that's 1.16, divided by h naught. And h naught is the speed of expansion of the universe, what we call the Hubble constant. Now, this is approximately 70 kilometers per second per megaparsec. And 1 megaparsec is a unit of distance, and this is roughly the distance from the Milky Way to Andromeda. So what this number is telling us is that the universe is expanding by a rate of 70 kilometers per second for every kind of section of space that's the distance from the Milky Way to Andromeda. Now, if we plug this all in, we put our 1.16 in here, we put our 70 down here, we put the speed of light here, we get a distance of 2.44 billion light years. So that is an enormous distance. Probably the most distant thing astronomers had detected at this point in time. It's kind of hard to understand how incredible this was for them to see, because this is quite bright. This is a quite bright little star. And actually what we work out is for this little point of light to be as bright as we see it from 2.44 billion light years away, it has to be shining out with a luminosity 20 times brighter than our entire Milky Way galaxy is shining out. All of those stars added up together, this little point of light is 20 times brighter. And we found quasars that were hundreds of times brighter than our Milky Way galaxy as well. The other thing is, this is really, really small. No matter how big of a telescope we zoom in, or we zoomed in with at the time, we still just see a little point of light. So it can't be very big. And actually we've seen that light varying over time. And the time it takes for the light to vary across the source, that puts a limit on how big it could be. For some quasars, we can see the light varying over hours or days. So they're going to be kind of no bigger than one light day across, which is about the size of our solar system. So we have something that is incredibly far away, incredibly energetic, and very small, the size of the solar system. We know they're also going to be very kind of sustained and not short-lived. And that is because of this little line here, this relativistic jet. So jet of material coming out from whatever the quasar is here. And the fact that it's a straight line means that it has to be sustained over the entire length. So this one here, this measures 200,000 light years across. So we know that something should have to sustain a jet emission for 200,000 years at a minimum. So these aren't transient events, certainly not in the way as supernova or gamma ray bursts might be, some of the other really bright things we see out there in the universe. We also know they're very blue, and remember from the spectrum, they contain gas clouds moving at enormous speeds. Later on, we've also found that they're not always a strong radio source. Only about 10% of quasars have radio emission, the rest of them are what we call radio quiet. It's just the ones that do emit radio light are very, very bright. So that's why we could kind of see these in the radio spectrum. So this is kind of the state of the quasar knowledge about the mid-1960s. We discovered all of these things about them, but we didn't really have a way to kind of understand what was going on. And that's kind of what I'll explain next. Do we have any questions at this point before we keep going? Yeah, over there.
On the slide where you have the spectrum of vega as well, the two spectrums. So one of them, the stars got two strong emission lines, and the quasars got two strong. Sorry, the stars got too strong absorption, and the quasars got too strong emission. That are separated for about the same thing. So it's tempted to say it could be the same elements redshifted. Is that the case?
That's exactly right. Yeah. So these are hydrogen emission lines, and these are hydrogen absorption lines. So the redshift here. Move that down, that. So yeah, these are the fingerprint of hydrogen, but we just didn't realise that at the time. Alright, any other questions, guys? Yeah.
Can you explain about the jet again? Because I know that like every time that the bigger the star is, the more mass it has, the brighter it is. Usually they die faster.
Yeah.
What does the jet have to do with the?
So first of all, this is not a star. At the time, we thought there were some kind of weird stars, but actually, once we get to the point of knowing this is billions of light years away, it's hundreds of times brighter than galaxies. That's definitely not a star. There's nothing like a star that can do this. So they didn't really know what it was. This jet is a hot jet of material. It's a relativistic jet. We find a few of these out there in the universe created in different ways. So sometimes we get them created by supernova, sometimes we get them created by gas clouds spiraling in a particular way, and we also get these from quasars themselves. I'll talk a bit about these in a couple of slides' time, but they're actually still quite mysterious in astronomy today. We see them out there in the universe, but we don't know that much about them. Certainly not how they're actually created.
Do we get them from pulsars?
Yes, we do get them from pulsars as well. Yeah.
Just to clarify, the jet that you were talking about in the lower image, is that the same as the jet in the upper image?
Exactly right. Yeah. Yeah. So I should have flipped it the other way, but yes, this is the jet here. This is the jet here. So this is not a background galaxy as they initially thought. So by the 1960s, this was our state of knowledge. Now, let's talk about the energy that we need. 20 times twice the Milky Way at least. How do we make this much energy? Certainly in a very small area of space. So first of all, let's talk about nuclear fusion. This is how stars make their energy. And what you do, very simply, is you take 4 atoms of hydrogen, and through this very complicated process here, you combine them into 1 atom of helium. Now, the mass of hydrogen is about 1.0073 in atomic mass units, and helium is 4.0026. Don't worry too much about what these numbers mean, but essentially, if we add 4 hydrogens together, we get more mass than the mass of 1 helium. So that extra mass has to go somewhere, and that comes out as energy. And we relate that by this very famous equation, E equals mc squared. So this is telling us that the mass here can be converted directly into energy, and kind of the ratio in which we can do it. So if we do this, we find out that the energy we can get from fusion, this excess mass, divided by the amount of mass we have available, gives us a conversion of about 0.6%. So nuclear fusion in stars turns about 0.6% of the mass of hydrogen into energy. And that's enough for stars to shine out with the enormous luminosities and powers that we see them doing. This is actually quite an efficient way of making energy. If we look at energy methods that we're more familiar with, like combustion, that's kind of 1,000 times less efficient than this here. So that's kind of why we're trying to do nuclear fusion here on Earth. It's not worked out yet, but maybe it will do in the future. But it turns out this still isn't enough energy to explain the enormous brightness of quasars. And by the end of the 1960s, a theory was kind of coming into place that might explain it. And the idea is we can create a lot of energy by taking a black hole. We take some stuff, let's say a gas cloud, and we move that gas cloud close to the black hole. Now, why does this create energy? Well, it's to do with the gravitational potential of this gas. I have my keys here in the pocket. If I hold them up in the air, they now have gravitational potential. And if I let go, they're going to fall to the ground. Now, they're being accelerated by the Earth's gravitational field. And as they get accelerated, they fall faster and faster. Now, imagine rather than a keys, we have an enormous gas cloud. Rather than the Earth, we have an enormous black hole. So this is going to accelerate gas faster and faster. It's not going to fall straight into the black hole either. It's going to spiral in and around. And all of this gas is going to rub together, creating an enormous amount of frictional forces and also what we call gravitational stresses. And this is just going to act to heat it up. If you imagine rubbing something together, it's going to heat up an enormous amount. And this turns out to heat the gas up to tens of thousands of degrees. Enough to make it glow incredibly brightly, indeed as bright as a quasar. So let's kind of imagine how much stuff will we need to do this? How much gas will we need to bring in close to a black hole in order to produce this enormous amount of energy? So first of all, let's kind of take a step back and talk about what a black hole actually is. So a black hole is a region of space that contains matter that is incredibly dense. So dense, in fact, that we model it in mathematics as a single point, smaller than an atom that contains 5 solar masses, or 10 solar masses, or 10 billion solar masses. Now, the closer you get to this, the stronger the gravitational field is going to be. And eventually, you're going to get to a point where it's so strong that not even light can escape. And this defines what we call the Schwarzschild radius. And this is kind of how we typically talk about the edge of the black hole. This is the part of space that's going to appear black around it, because once light enters here, it cannot leave. Now, we can't bring stuff all the way into the black hole. That's going to just fall in, and by that point, it already won't be emitting the light anymore. So, we're going to use this equation here. This is the energy given by the gravitational constant. This is just a number. We have the mass of the black hole, the mass of the stuff we're putting in, and the distance we're going to bring it into. And this is the radius of the last stable circular orbit. As stuff comes in, it's going to spiral around that black hole. The spiral is getting smaller and smaller as it circles in, and a little bit like falling down a whirlpool, until eventually that spiral kind of breaks down and it just falls straight in. So that happens at this point. So if we put this radius in this equation, and we cancel out numbers, cancel out the letters, we get E equals mc squared over 6. So mc squared, this is our energy mass relation, and it's 1 over 6. That is telling us that we can convert 1/6 of all of the energy of that stuff that's, or all of the mass even, of that stuff that's falling into the black hole straight into energy. So this gives us an energy efficiency of 16%, tens of times better than nuclear fusion. And it turns out for certain types of spinning black hole, this can be up to 45%. So it is one of the best ways, if not the best way, to extract energy in the universe. And if we crunch the numbers, it turns out if you take a black hole, the same size as the one in 3C273, and you feed it 1 solar mass a year, so a cloud of gas, the same mass as our sun, that will produce the light of 100 Milky Way galaxies. So we produce a lot of light very, very easily. And by the time it got to kind of the early 1970s, this wasn't very well accepted because black holes were seen as a very theoretical concept. We weren't 100% sure that these things actually existed or whether they were just going to be a quirk of mathematics. But by the time that kind of this period came around, we had X-ray telescopes in space, we had better understanding of cosmology, and slowly astronomers began to agree this is what we were seeing. So, let's talk about what actually is a quasar. Well, it looks something like this. We have a few different features to unpack. First of all, let's talk about the black hole in the center, this little thing right here. Now, we've already talked about what a black hole kind of is. There's different types of these black holes out in the universe, though. They're pretty much the same thing, but we just find them in different sizes. So, for example, if a star 20 times the mass of our sun or larger dies in a supernova explosion, that's going to create what we call a stellar mass black hole. A black hole somewhere between 5 and 50 times the mass of our sun. So that's really, really heavy. There's a lot of stuff there, but that's not big enough to form a quasar. We need much stronger gravitational forces. We need a black hole that weighs millions or billions of times the mass of our sun. So where do we find one of these? Well, it turns out we think there's one of these supermassive black holes in the center of every galaxy in the universe, our Milky Way included. So in the center of our Milky Way, there is a black hole named Sagittarius A star that weighs 5 million times more than our sun does. So there's quite a few of these out there. In the center of every galaxy, there's 2 trillion galaxies in the universe, so there's going to be trillions of these supermassive black holes. Then the supermassive black hole is feeding on material. There's gas that's spiraling in towards it, and this creates the accretion disk around it. This is the stuff that's experiencing these enormous gravitational forces, accelerated to tens of thousands of kilometers per second, and are emitting all of this light. So because they're glowing so hot, they're glowing really blue, and they're glowing in the ultraviolet as well. That's why these quasars look really blue when we see them from Earth. Then if we get a little bit further out, we have this ring of dust surrounding the central engine. This is what we call the dusty torus, and it forms a bit of a donut shape. Now, we're not entirely sure where this comes from, I think most astronomers kind of presume that it's gas that's being driven in towards the quasar by the galaxy. So maybe in the future, the stuff that's around here could become instant centered and being eaten by the black hole. But this is quite important in actually how we see quasars, because if we view it from the side, this gas can actually block the view of all of this light that we're seeing from the middle. And like I said, these are often modeled as these donut shapes, but we know that they can come in all kinds of different shapes and sizes as well. So then, jutting out from the black hole in the center, we have this line of light. This is this relativistic jet that we saw in that image of 3C273. So once again, these are really mysterious things in the universe. We see them, we kind of understand a little bit of how they're made, but our physics is very incomplete. We think there's something going on with the accretionist here, is swirling around and is generating a really strong magnetic field. That's going to accelerate away particles in this relativistic jet. And we do see that the stuff that's in this jet here is traveling at nearly the speed of light, so incredibly quickly. And then we're going to have some clouds of gas and dust surrounding the quasar as well. And this explains the broad lines and the narrow lines that we're seeing as well. So the broad lines are coming from the very center here, around the black hole. That's where the gas is going really, really quickly. It's heating up, and we're seeing these really strong, broad emission lines. Then a little bit further away, we have gas clouds surrounding the area that are moving much more slowly because they're a bit further away. And this is where we're getting the narrow lines, where these are being excited by the energy from this jet. So there's a lot going on here. There's a lot to unpack. And all of this kind of comes together into an object that we call an AGN, or active galactic nucleus. And we see a lot of these things out there that aren't necessarily quasars. So in general, an active galactic nucleus is a compact region at the center of a galaxy that emits a significant amount of energy across the entire electromagnetic spectrum. And this is going to be much, much brighter than what we can explain just with the emission from starlight alone. Now, one of the earliest AGN to be discovered was Seyfert galaxies. So that's what we have in this image over here. Now, on the left, we have Seyfert galaxy NGC 5548, and on the right, we have a normal galaxy, NGC 3277. Now, these galaxies have been chosen because they look pretty similar to each other, and apart from, if you look right into the core here. So if we look for the galaxy on the left, we see it is a little bit brighter. Actually, with the camera detection, this is much, much brighter. And we're seeing these spikes across it as well. These are diffraction lines. They are caused by the telescope design, but we only see these when we're looking at a really, really bright source. So astronomers observed these galaxies that have very bright cores and very strong emission lines. And the first one was detected in 1908, and by 1943, a catalogue had been put together of about 7 of these by a guy named Seyfert, so that's why they are Seyfert galaxies. And this is just one type of these AGN. We have a little list here. We have Seyfert 1s, Seyfert 2s. The difference between them is Seyfert 1s, we see broad emission lines, Seyfert 2s, we don't. But then we have quasars, blazars, and BLACs, and all of these weird, wonderful things. Here is a much more complete table. It's a bit fuzzy, but hopefully gets the point across. There's lots of these different types of AGN out there in the universe. Quasars are just forming one kind of section of what we think these things could be. Now, let's have a look at this in here. Let's look at blazars. So this is actually a subset of quasars. We're seeing this kind of thing, but we're seeing this relativistic jet face on. So we're looking top down over the quasar, and this is pointing straight at us. Now, this is an incredibly intense beam of charged particles and radiation. And so this doesn't spread out as much over the universe as it travels. So we see these blazars much, much brighter than actually if we weren't looking directly onto the jets. These are the brightest AGN we see in our sky, certainly brightest in terms of the intrinsic luminosity that we can detect. And this is actually kind of compounded by the fact that the particles here that are emitting light are traveling at nearly the speed of light themselves. So we get an effect from relativistic beaming, which just means because they're traveling fast and we're not, we see that light a good few hundred times brighter than it would be otherwise. So we know that quasars and blazars are kind of subsets of the same thing, viewed from different angles. So we can kind of imagine doing this with the rest of these objects. And the simplest way to think about this is by thinking about one great big central engine, which is, as we've described, a black hole feeding on gas with dusty force around it, and maybe a jet or maybe not a jet, And we're looking at this at different angles and we're seeing different characteristics from this system. So for example, super-1 galaxies, looking down onto the quasar, we're seeing this broad line region here, we're seeing all the other features. C2 is maybe we're looking in from the side, so we're seeing some of the other features, but this broad line region is being absorbed by the dusty torus, so we're not seeing that. So this kind of idea works really well for unifying certain types of these AGNs. So C1, C2, quasars, blazars, BL-lax as well. All of these we're pretty sure are the same thing used from different angles. But there's a lot of nuance going on here that we don't really understand very well at this point in time. So the shape of this dusty torus, that can influence what we're seeing, as can the exact chemical makeup of the gas clouds, as can the size of the black hole, and actually how fast it's feeding. All of these things have an effect. And so there's lots of these things that we've not been able to unify simply because we don't understand exactly what's going on here in enough detail yet. So hopefully in the future we'll have better simulations of how quasars work, and we'll have better observations as well, and this will let us unify more of these different AGN together into one kind of really cool thing. All right, so I'm going to pause here again. Does anyone have any questions about what we're talking about? Yes, in the back.
Yeah, so the jet emission is usually in both the sides or just one?
So it will be both sides, but what this diagram is showing us is actually two different circumstances. One where we have jet emission and one where we don't. So if we have jet emission, that's where we see all of these different things. If we don't have jet emission, that's where we're going to see C1s and C2s.
Otherwise it will just be an entire circle, but the information will be like the mirror images.
Yeah, so if I go back here, like this graph here, we're going to see jets up and jets below as well, but we don't always see jets. Now, why that is, we're not really sure. Once again, jets are pretty mysterious. We don't know why we get jets created sometimes, but not other times. But we do know we don't always see them, and this is going to kind of go into some of these different objects. Any other questions? Yeah, back.
It's a bit of a stupid question, I got lost in the way. But if it keeps sucking up things,
Yeah.
why is the jet ejected? Like, how
So,
does it happen?
the jet is outside of the Schwarzschild radius of the black hole. So we have the black hole here. This is this little black circle. That's the point at which light can't escape. But this jet is actually forming outside of that. So light and particles and whatever can escape at this point if they are traveling fast enough. So we think the jet isn't being created by the black hole itself. It's being created by the accretion disk, this hot ring of material that we have around it. So that is somehow creating this jet. And so, given that it's not happening within the black hole, we can still see it. Stuff is still able to escape. But exactly how that is created, we're not sure yet. All right. So we think we can unify a lot of these AGNs out there in the universe. And when we're looking for them, we have found over 1 million AGN and quasars out there, kind of among the cosmos. But we don't see them uniformly all over. So if we look in the local universe, we see within 600 million light years, there are 650,000 galaxies. But we find just one quasar. So that's kind of looking at this graph down here. We have the number of quasars, or number of AGN that we have up here on the y-axis. On the x-axis, we're looking at increasing redshifts. So this is increasing distances, but also looking back in time as well. If something's 100 light years away, light has traveled 100 years to reach us, so we're seeing it as it was 100 years ago. Now, if we're looking at a redshift of 2, we're looking about 8 billion years ago, when the universe was just 3.7 billion, 10 billion years ago, when the universe was just 3.7 billion years old. So we're looking back in time, and we're seeing, as we look back in time, we have this massive spike of the number of quasars and AGN discovered. So these are things that were around in the early universe, but don't seem to be around today. So can we try and explain why this has happened? Well, one thing that might help us is this image up here. This was taken with the Hubble Space Telescope, I believe, in the early 2000s, and what we're looking at are quasar host galaxies. So we have these really bright central regions, this is where we're seeing quasars, and then we have this kind of dusty light around them, that is the galaxy. And this has taught us a lot about actually the formation of quasars, because we see a lot of dramatic, violent events happening in these galaxies. Here, we're seeing two galaxies merging together. Again, two galaxies merging. In this one as well, we've got this little filament coming up here. We've got this big ring around it. This suggests a very recent galaxy merger, as does this one over here. So mergers seem to be a really important factor for quasars kind of being able to exist. And this is because we need this dust, we need this gas to be driven into the center, to the black hole, where it can swirl around, heat up, and produce the light as we're seeing it with our telescopes. And the universe today is just too calm, it's too settled. There's not enough of these mergers, and there's not enough of these dramatic events. So that's why we're not really seeing so many of these quasars today. But what about this section over here? The further back we look, the less quasars we find as well. So there could be two things going on here. We could be seeing actually that these quasars are just a bit further away, they're a bit too faint, so we're going to have more trouble spotting them. But also, we have the issue of the black hole in the center. And to demonstrate this, I'm going to talk about this AGN, this quasar over here. Now this happens to be the most distant quasar that we've ever found in the universe. So we've got quite an interesting image here. We have a galaxy supercluster called Able 2744, and all of these little kind of fuzzy points of light, these are all galaxies. Apart from this one here, this is the foreground star. And then that is a James Webb Space Telescope image, by the way, and then overlaying over the top of that we have this purple light. This is from the Chandra X-ray Observatory. So this is a space telescope that looks at X-rays, and what this purple light is telling us is that there is hot gas present in these regions. So as we zoom in on this area, we find a little galaxy, and then in the James Webb image, a very, very faint little dot of light. That is a black hole host galaxy. If we overlay the X-ray emission over the top of it, we see it's glowing really brightly. And this is a characteristic feature of an accreting supermassive black hole. So this is an AGN, or a quasar, forming in the center of here. Now, we can look at this luminosity, and that tells us that we have a 40 million solar mass black hole here, an enormous black hole here in the center. But this is so far away that we're seeing this kind of occurring as the universe was just 470 million years old. So in 470 million years, how do you get a black hole that is big enough to form this kind of quasar activity? Because our current understanding, or our old understanding of black holes, I should say, is that we get stars dying, forming these stellar mass black holes, which come together over time and then feed on gas with quasar activity to grow until they become supermassive, so millions or billions of times the mass of our sun. But actually, if we try and model how this could work, and we have a few of these little black holes coming together, growing over time, it's really hard to come up with a scenario in which we have a 40 million solar mass black hole in place when the universe is this young. And so it's thought that maybe this isn't what we're going to be seeing. Maybe rather than stellar mass black holes, we have to think a bit differently. Maybe we can produce black holes in other ways. So this is a really cutting edge field at the moment of trying to work out how these black holes can form. One idea is maybe we have enormous gas clouds that skip beam stars altogether and then just collapse directly into black holes. And this can form black holes that are tens of thousands of times the size or the mass of our sun, which is much, much bigger. And then we can imagine these accreting over time to become this big after 470 million years. Another option is maybe there were black holes created in the Big Bang itself, what we call primordial black holes. We have no evidence that these exist, but maybe this is our first clue. So this is a hint of kind of how important quasars are, because they can tell us so much about the universe. Here we're learning about how these supermassive black holes actually form, and this is going to tell us so much about structural formation and the conditions of the early universe as well. Now, another role in which they are incredibly important is in galaxy evolution. Almost every galaxy around today has been shaped by an active galactic nucleus in its past. One great example of this are elliptical galaxies, these great big blobs of starlight. These are some of the largest galaxies in the universe, but they are incredibly boring. We call them red and dead because there's very little star formation going on here. There's just a bunch of aging stars, there's no gas or dust, there's nothing that can form stars again in the future. But if you take an enormous gas cloud and you form a galaxy out of it, it's not going to form one of these. It's going to form one of these, a spiral galaxy instead, like our Milky Way. And so, if you want to get an elliptical galaxy like we see in the universe today, we have to imagine spiral galaxies merging together in a dramatic splash of all of these different stars, gas clouds coming together, and then they lose their structure and form one of these great big boring balls instead. But if we model this and we find out that the spiral galaxy has gas in it still, then it's not going to form necessarily an elliptical galaxy. It can come back and form a spiral galaxy again. So for our observations to make sense, we need a way for these spiral galaxies to lose a lot of their gas content before they merge. And quasars and AGN are one of the best ways to do this. So when quasars interact with their galaxies, we call this feedback. And one of these feedbacks is outflow. So you have your AGN here in the center, your active galactic nucleus. You have this cool gas around it. Now, as it's feeding, it's kicking out this enormous amount of radiation and energy. And this is going to act as a force on a lot of the gas that's around it that's not spiraling into that quasar. And it's going to push it away from the galaxy. And through our simulations, we found out this is actually a good way of driving gas out of the galaxies that the quasars are part of. Now, another thing quasars might help us understand is why we don't see lots of really massive galaxies containing lots and lots of stars today. When we're looking back at really distant galaxies, when we're looking back in time, we see there's lots of gas and dust available for star formation. But when we look at galaxies that are close to us, we see that there's not as many stars there as we'd expect. So there's something happening that should be stopping star formation happening. And that is again explained by quasar heating, or AGN heating. So we have our AGN in the middle of the galaxy. It's surrounded by cool gas. Now we need cool gas to form stars, because if the gas is too hot, when we try and collapse it down to form a star, it's going to push back with pressure, and that collapse is just not going to happen. So we need cool gas to form stars, but the AGN is going to heat its surroundings by kicking out all of this energy, and so it's going to turn that cool gas to hot gas over time. And this is going to explain why we're not seeing as much star formation as we might expect. So, just a couple of examples here. There's lots more going on with the feedback and how it kind of affecting the galaxy as a whole. Sometimes this can actually increase star formation as well in very specific circumstances. But this is just one of the ways that quasars are really, really important. And another one of them is actually using them as background light sources. Because quasars are so far away, we can use them to study everything that's lying in between us and those sources of light. So for example, if we look at this image here, we have a background quasar. The light is passing through the universe, and it's going to pass through a lot of intervening gas and dust, the kind of dark star-forming stuff that isn't visible, but that we want to know lots about, because we want to kind of understand how stars, galaxies, and star clusters form in the early universe from this gas. So as the quasar light passes through it, we're going to get lots of these absorption lines. We've got dark clouds of gas absorbing the light. We're going to get all these little dips that we're seeing here. Now this is called the Lyman alpha forest. And the reason we're seeing a forest is because we have these little lines, and each gas cloud that the light passes through is going to give us one of these lines in the spectrum. But all of these are at different redshifts, so we're seeing them at different points in the spectrum as well. So when we get a feature like this in the spectrum, this is not just telling us about one gas cloud. This is telling us about every single gas cloud in between us and that quasar. We're getting a cross-section of the entire universe. So this is a really, really powerful tool for astronomers to study anything from star formation to galaxy mergers, and even looking close to home. So one way that this is used is to study the Large Magellanic Cloud. This is a dwarf galaxy on the edge of our Milky Way, about 160,000 light years away. And this is a survivor. It's not used to be around our Milky Way. It has come in close, and as it does so, it's moving through the really diffuse medium surrounding our galaxy. This big cloud of intergalactic gas. This is putting a pressure on the front of the Large Magellanic Cloud, and it's washing away all of its gas and dust. Our Milky Way is stripping it of its material. So we had an idea that this was happening from observing other galaxies, but this dust isn't emitting light, so we can't see it with our telescopes. But what astronomers did instead in one study is they looked at the light from 28 different background quasars, and we see the absorption lines from this gas and dust around the Large Magellanic Cloud. And that's allowed us to trace out the path of this through the sky and through the universe as well. So this is really important because we're studying our local universe, we're looking at our neighbour in the sky, but also this is a great laboratory for us to study how galaxies merge over time as well, and what might happen to all of the gas and the dust content as these mergers happen. So quasars, just as distant lighthouses, are increasing our understanding of the entire universe. And the final method that I'm going to talk to you about, which is probably equally as important as this, is actually using quasars as enormous rulers to measure the universe. Now, we've already talked about distances to quasars, and we've talked about this using that redshift Hubble constant relation. But we have to work out that Hubble constant. It comes from the fact that we see this relation between distance and velocity of stars, galaxies, and gas clouds out there in the universe. But this has been called into question recently. We're able to measure this by different methods, and the methods are not agreed. This is called the Hubble tension, and is a major crisis in cosmology at the moment. So, if we wanted to maybe resolve this, or at least be able to measure accurate distances to the really, really distant universe, quasars might be our solution here. So when we're measuring distances, we build up what we call the distance ladder. So for anything really close within our solar system, we can use radar ranging. But the closest star to us is 4.4 light years away. So if we're going to do this, we have to wait 9 years for a return on that signal. That's not going to be useful. But luckily, anything within a few hundred light years, we can actually detect by a stellar parallax. So as the Earth orbits around the Sun, that difference in position is changing our perspective slightly on the galaxy. So for the very close stars in the sky, we're going to see them wobble ever so slightly as we complete a year's orbit. If we can measure the size of this wobble, we essentially can use trigonometry in order to work out the distances to those stars. So then, as we get further away than that though, these wobbles are just too small for us to be able to measure. So then we have to build up a relation between the properties of something that we're observing and its intrinsic luminosity. And variable stars are one example of this. These are stars that vary, they pulsate with brightness. And if we measure this pulsation and we time it, it can tell us a lot about the properties of that star. We can use that to work out the intrinsic luminosity, and so we know the further away we are from something, the more that light is going to spread out. And we can use this flux luminosity equation here to work out the distance to that source. And then we can do the same with galaxy rotations and supernova. And this gives us an upper limit of about a few billion light years away that we can measure. Any further than that, we're going to have to rely on that Hubble's law. But maybe quasars can extend the distance ladder. Maybe we can use these up to maybe 30 billion light years away. And that's because quasars have a very tight relation between their ultraviolet luminosity and their X-ray luminosity. So that's what we observe here. We have ultraviolet light here, X-ray light here, and we see this nice straight line. So if we can measure the ultraviolet and the X-ray luminosity of a quasar, we can use that to work out its intrinsic luminosity, how bright it should be if you are standing right next to it. And then we can use this principle here of light getting fainter over time and distance to be able to work out the distances to these quasars. So maybe measurements of the universe of quasars in the future will help us resolve the Hubble tension and actually teach us a bit more about the very early universe and the expansion history of our universe as well. So that is pretty much it for everything that I have about quasars for you guys tonight. There is a whole lot more to talk about. These are really, really important things out there in the universe. I could keep going for hours and hours on this, but I'm sure more of you would fall asleep if I did that. So let's talk about the future of quasar study. So there are a lot of open questions. Because these things are so far away, and because we only discovered them and worked out the theory about them relatively recently, there's so much that we don't know. So I've already covered a lot of these things, but quasar jets is one. How are these made? How do they work? This is stuff that we still need to find out. We need to also want to find out what is producing the different types of active galactic nucleus. Are we looking at the same object at different points in time, or from different perspectives, or with different compositions? How do supermassive black holes grow so quickly in the early universe, and what is that going to tell us about the universe as well? And then, we didn't talk about it really, but the effects of black hole spin as well, and finally the effects of quasars on low mass galaxies and AGN feedback, and so on and so on. There's so much that we don't know out there, and so quasars are still a really kind of cutting edge area of astrophysics research. One of the things that could help us out here are numerical simulations. So as we get better and better computing power, we can simulate how quasars might look and might work ever more accurately. We can't build a quasar in the lab, that just doesn't work. So this is the best way we can kind of model what's going on. The other thing we can hope for is better equipment and better observations as well. So hopefully everyone here has heard of the James Webb Space Telescope that was launched a few years ago, and that is already revolutionising certain areas of astrophysics today. Now, one thing the James Webb Telescope can do really, really well is look at infrared light. So light that's been redshifted to no longer part of the visible spectrum, and we can use this to find really distant quasars and find their spectra very, very precisely as well. So this is helping us probe the oldest and the faintest quasars of the universe. A telescope that's being built here on Earth in Chile, in the Atacama Desert, is the Vera Rubin Observatory. So this is hopefully going to be completed and have its first light this year. And this is a telescope that's going to survey the entire sky once a week. And the goal is to find things that are transitioning or changing through our night sky over that time. So this could be asteroids which are slowly moving, which we've never found before. It could be a supernova which suddenly appear and then fade out over time. But maybe this could help us find stuff out about quasars as well. One idea is that quasars are variable, they change brightness over time. And maybe this could help us measure that quasar variability. But probably the most promising piece of technology is going to be this one here, the Extremely Large Telescope. Now, as the very creative name suggests, this is an extremely large telescope. The primary mirror for this thing is going to be 39 meters across. For context for that, the largest optical telescope we currently have in the world at the moment has a mirror that is 10.4 meters across. So this is going to be 4 times bigger than any telescope that we have today. And it's hoped that this will be able to peer out at the really distant universe, find quasars like James Webb has done, but also be able to analyze them in a much more precise way than any of these other telescopes ever could. It's going to have an enormous ultra-precise spectrograph with it, so by seeing all of these emission and absorption lines in really, really high detail, that should hopefully find features in the spectrum that we've never found before, and hopefully explain a few more of the things that we're seeing out there. So, that does bring us pretty much to the end of the talk. Thank you guys for coming along. Hopefully, you now know a little bit more about quasars and how they are really important for us in astrophysics today. Amazing. So, does anyone have any questions before we head on out? Yes, over there.
There was a graph at some point with showing the amount of quasar we found with distance.
Yes.
And so I understand that we find less and less as there are less galaxies available to collide. But the drop seems pretty abrupt.
Yes.
Do we have any, like, that's surprising in any way? Because you would expect something to be a bit more smooth.
Yeah, I'm not really sure actually why there is such an abrupt drop. That's a good question. I guess maybe as we're looking at further redshifts, the universe is kind of exponentially smaller over time. So the universe is actually growing quite a lot bigger in this gap than it is in this gap here. So maybe that's kind of, it's been a very big difference, and now that's going to give us a very big difference again with kind of how we're seeing these quasars. It could also be that maybe the certain amount of material that we have in a galaxy that's going to be pulled into the center and absorbed by this black hole. Maybe just after this amount of time, then there's just not going to be that material around anymore. So I'm not sure, but that's kind of where I might imagine to go. Yes, there in the back.
Yeah, I don't understand what the numbers on the horizontal axis represent. 13.8 to 0.68 I understand, but the numbers 0.0 to 7.5, I'm not very sure I got that.
Yes, so this up one here, this is Z, this is the redshift. So this is the factor by which the light has been stretched out. So if we see a line that is redshifted by a factor of 2, it is kind of double the way down the spectrum from where we expect to find it. So we just measure how these lines have moved, and this gives us this factor of Z, and then this corresponds to distances and also the age of the universe as well. Right, yes, there in front.
There was a plot that you showed with X-ray luminosity compared to ultraviolet luminosity.
Yeah.
So just trying to understand the units here, you have ergs as like energy, right? So
Yeah.
you have energy per second
Yeah.
per hertz.
Yeah.
So that hertz is the frequency of the center that you're observing with, or is it the
Yeah,
frequency of like the whole bandwidth?
So what they did in this study was they took one specific frequency or one specific wavelength of X-ray luminosity, and then one specific frequency of UV luminosity. And their justification for that was, we just picked them. So we think there's some kind of central process that producing both X-ray and UV light. For us to observe this correlation, that must be true. So the astronomers that did the study, they said we can just pick any part of the X-ray spectrum and we'll find a correlation with any part of the UV spectrum. So this is only looking at one specific kind of frequency and one specific frequency of the X-ray as well. Does that kind of make sense? Yeah. Right. Yeah, at the back.
Why is the extremely large telescope being used?
When will it be used?
Yeah.
So it's currently being constructed. It doesn't look like this. This is model. So all of the kind of building is in place. They're building these big flaps at the moment. The mirrors are being created as well. It's being assembled at the Parallel Observatory in Atacama Desert in Chile. And the hope is by 2030 we'll have the telescope up and running. As with these things, there's often delay after delay after delay. I think the James Webb Telescope was delayed something like 15 or 20 years. So let's hope it does happen 2030, but I don't think we should get our hopes up. It might happen a little bit after that. Right, any other questions, guys? Right. So at that point, I'll put the lights on. Thank you so much for coming along tonight. You've been an amazing group. Thank you for your questions. I'll be hanging out at the end, so if you guys want to come up and ask me anything in 2 minutes.